Good morning. I am Marita Kotze, Senior Education Specialist for Physical Sciences from IMPA. We're going to give you 2 minutes just so that all the learners can log in, that register for this session. In the meantime, I just want to see if you can hear me. By putting up your hands, you can just show me if you can hear me. You can see there to the right or below there are a box. You can choose a hand to click on the hand and just show me if you can hear me. Okay. Yes. Thank you very much. Yeah, I do have 2 hands. Thank you for that. Right. I'm clicking on. Yeah. Thank you very much. Thank you for that. All right. Just another minute. Okay, while we're waiting, I will say that again, but if you do have any questions, please remember to write your questions and download, write your questions in the question box and download all the notes in the handout box. Please make sure that you do that. Just a few more seconds. Okay, good morning. I am Marita Kotze. I am the Senior Education Specialist for Physical Sciences at IMPA, and I will host this webinar today. All right. As my previous last week, I hope you are still busy dreaming about your career and using physical science to get there. This is an article. It is, as you can see, the blocks that you see here, the letters are cut out of ice cubes. So you'll start dreaming about your career in physical sciences. Okay, I am Marita Kotze, Senior Education Specialist for Physical Sciences. And before we begin this webinar, let's cover some of the basics. We will deal with your questions after the session. I'm not going to answer any questions during the session, but you're welcome to write a question in the question box. Please feel free to do that. Or if you do have any suggestions, you can also do it there. Then there are handouts. The handouts today are examinations about the topics that we cover today. So make sure that you download that. Now the memorandums of the examinations are loaded on our guided learning platform, so you can download it. And if you're not registered with IMPACT, you can send an email at info@impact.co.za. So make sure that you download the exams so that you can start looking for those questions. Okay, if you do have any question and you didn't write it in the question box, you can send an email to academics@impact.co.za. And feel free to make any suggestions if you want to. So memorandums and PDFs of today's session and the examinations will be on the guided learning platform, and you can visit the IMPACT YouTube channel for the recording of this session. Today we're going to do chemistry, And the knowledge area that we're going to cover is chemical change. It is topics that you are still busy with during this week, so and until the exams. So I did cover some of the content, not all of the content. So I will cover some of the other content during our next session. But in the meantime, if you do need more information than what I'm going to cover today, you can also download science student notes, but more about that later on. All right. One of the topics that we're going to cover is equilibrium and chemical reactions. That's one of the topics that the calculations of equilibrium I will cover next in the next video. Okay, acids and bases. That's also part of the June examination. If it's still going to go through, we're not sure what's going to happen. Okay, and then rate of reactions. Okay, rate of reactions is the first topic that we're going to cover. Okay, what is the rate of reactions? It is a measure of how fast the reactants are converted to products. As you can see here, there are products inside this bulb, and there's a chemical reaction that's busy taking place at a high rate. So that is the one or two or more, or the two or more chemicals that are busy reacting inside this flask is it's busy taking place at a high rate. Okay, what is the collision theory? The collision theory is used to explain the steps atoms go through as the arrangement changes from reactants to product. I just want to say this. Say, for example, if you want to make natural table salt you use in your everyday life, and the chemical formula for that is sodium chloride. Now, if we think about sodium chloride, sodium is a metal. It's an alkaline metal. It's a soft metal. It's a solid. And chlorine is in its normal state, it is a diatomic gas. And if you smell it, you will cough a bit if you inhale it too fast. So yeah, chlorine gas with sodium chloride, it's a solid and a gas that must form table salt. That's natural. That's sodium chloride that I eat on my food. So I'm not sure how that go off with you, but thinking about that, wow. So what must happen with these two reactants to become a product, sodium chloride? Particles must collide with sufficient energy. Particles must collide with the correct orientation, and bonds in original molecules must break and new bonds must form. So yeah, the bonds in the diatomic molecule and the bond in the metallic structure of the sodium must break before anything can take place to make stable salt. So some collisions are effective and others not. I do include here a visual thing so that you can see. Here we have water and we have hydrochloric acid. Can you see there's hydrogen and chlorine, and they need to combine. Now here there's a collision that's taking place, and after the collision nothing happened. Why do you think? Because there on this side there's a high electronegativity side. It's a covalent bond, and the covalent bond on this side is the negative pole. All right. So, and here is the negative pole of the chlorine, and can you see it's big, so it clashes and just go in each of them are going in another direction. So when an effective collision happens, what is going to happen? There must be a correct orientation. Can you see here? It's the hydrogen. It's the positive side of this dipole and the negative side of this dipole. Can you see? And here there will take place a hydrogen bond between the hydrogen and the oxygen. So when the collision takes place here, you can see that after that you have an hydronium ion, H2O positive, and a chlorine. So this reaction here is successful because the orientation was correct and it collided with sufficient energy. So this collision was good enough. So why the collision theory? If there is not sufficient energy and there is incorrect orientation, regional bonds in molecules didn't break. So there must be, why will there be not effective collisions? If it's not sufficient energy, incorrect orientation, then you don't have enough bonds that break. All right. What is the Maxwell-Boltzmann distribution curve? Now this curve shows the distribution of the kinetic energy of molecules for bonds to form. So here we have the number of molecules, increase in the number of molecules and energy per molecule. Can you see the area under the graph to the right of the activation energy line? Here is the activation energy line. It's molecules with enough energy to react. And you see there's a small amount of molecules that do have enough energy, kinetic energy, for an effective collision. This curve shows therefore a small fraction of molecules that have enough energy in order to collide and form a new product. Okay, the effect of temperature change. Let us just look now. Okay, here we do have a lower and a higher activation energy. So as the activation energy of a reaction decreases, the number of molecules with at least as much energy increases, as shown by the shaded area. All right, so if you do have enough energy, what is happening with an increase in temperature? With an increase in temperature at a higher temperature, more molecules have enough. More molecules have enough kinetic energy greater than the activation energy, as shown by the yellow shaded area, and more effective, that yellow area there. Okay, so more effective collisions can take place in order for the reaction to take place. So, how do we measure reaction rates? Okay, because we do experiments, and how do we measure it if it's a good or a bad reaction that happens? Okay, we one of the things is if we use, for example, magnesium and hydrochloric acid, sulfuric acid. If we use this metal and sulfuric acid to get a salt and hydrogen gas, okay, the hydrogen gas can be measured by collecting the gas in a syringe, and you can take the time that it takes for the hydrogen gas to form. So in this container, can you see this is a closed system? We have the magnesium and the sulfuric acid that's busy reacting together to form hydrogen gas, and then the salt, can you see there the salt? The salt is busy forming. So, and that we can do a graphically presentation. As you can see here, the volume of gas that formed during a certain time. In the beginning, it was the fastest reaction rate. Can you see there's a steep gradient at the start, very steep gradient at the start, and then the gradient decreases with time as the reaction rate slows. And then at a certain time, the gradient becomes 0. Why? Because the reaction stops. No more gas is produced because all the chemicals, or in any case, one with the that's not in excess. The other one, the limiting reactant rule, in any case, we already done with the reaction. So yes, something else must happen before we can have turbine. Good. So yes, so we can collect the gas and we can put it in a graph to show the reaction rate or to measure the reaction rate. Factors influencing the rate of reaction, there are four things. The nature of the reactants, in other words, is it small particles, is it big particles, and the surface area of smaller particles, there's a bigger surface area, smaller because there's more surface area that's exposed to the, in this instance, if we use smaller particles like magnesium, uh, uh, fine magnesium, magnesium power instead of magnesium rivet, then the reaction will take place much faster. So the concentration of the reactants is only for gases and solutions only. Increasing concentration of the solution increases the chance of collisions. So, for example, for using an acid with a higher concentration, the reaction rate will increase. Excuse, sorry about that. The other thing is temperature. If we increase the temperature here, the reaction rate will even be faster here. So by increasing the temperature, the kinetic energy increases and more sufficient energy for more effective solutions. Therefore, the action rate increases. Catalyst is always something. What is a catalyst? It's something that is present in a chemical reaction that increases the reaction rate, but does not take part of the reaction. It doesn't form anything at the end. So the catalyst decreases the activation energy. Sorry about that. More particles have sufficient energy to overcome the low activation energy. Therefore, we have more solutions and the reaction rate increases. Now, let us just look at, we do have here small particle, big particle. Can you see here? Small particles, big particles. The volume is the same. So the volume is constant here. And we have two graphs here. It is at the same time, we have flask 1 and flask 2, and they're taking place at the same time. All right, so what is happening here? Both of them start at the same time, and the reaction rate of one is much faster than the other one. So few times before the bigger particles take a bit to before it started to light, and the reaction can actually take place. All right. So concentration of reactants. Concentration of reactants, if we do have concentration of, say for example, we have hydrogen gas here, and we have iodine gas here, and in the beginning, we only have hydrogen and iodine gas. Nothing, we don't have any hydrogen iodine formed yet. So we put the hydrogen gas and the iodine gas in a container. So we're in a closed container, and the moment it started to happen, as the reactants decreases, the products that in this case the hydrogen iodine started to form. Okay, can you see in the beginning it's a steep gradient and then slow down, and you can see there it is, a Fabry gradient. So yes, and there you have At that stage, it's equilibrium. More about equilibrium later on. So we have hydrogen gas and iodine gas, of course. Hydrogen, iodine. The gradient of either curve will give the average rate of the reaction for the time interval, delta T. So, how will temperature, the third one was temperature. Let us look on the graph, the Maxwell-Boltzmann graph. What happened here? Can you see in the first place, we do have 20 degrees Celsius. We have the temperature is 30 degrees Celsius, and the activation energy that we do have here is the threshold energy. Twice as many molecules possess the threshold kinetic energy at 30 degrees Celsius. The threshold kinetic energy at 30 degrees Celsius is the molecules that do have enough energy to collide for the reaction to take place. All right, the fourth one was the catalyst. So what is happening with the catalyst? Here we can see a catalyst. What is happening here? The exothermic and endothermic curves and the activation energy we'll do in the next webinar. But for now, as long as you know that we have a catalyzed reaction and an uncatalyzed reaction. Can you see in the catalyzed reaction, we do have less activation energy as we saw in the previous slide. We have less activation energy here, but we have more molecules. Right. Less activation energy, more molecules. Okay. A catalyst always lowers the activation energy, and so more molecules have sufficient energy to make effective reaction. All right. If we look at the measuring rate of a reaction, what is the measuring rate of a reaction? The measuring rate is usually measured in moles per second, and we use experimental data to determine the rate of a chemical reaction. Here we have the reactants and the products. If we want to know the rate of the reaction, we take the change of the reactants divided by the time, or the rate of the reaction. If we want products, is the change of the product divided by the change in time. So here we have an example, and we ask, calculate the rate of a reaction if it takes 18 seconds to produce 42 moles of carbon dioxide from a wooden fire. Okay, 42 moles divided by 18 seconds is 2,3 moles per second. The next topic that we're going to cover is equilibrium and chemical reactions. This is quite hilarious to me because here we do have, can you see, in both we do have the closed system and the one molecule say to the other molecule that's the same. I'm sure glad they evaporated. Can you see there? They form gas molecules. So yes, now the one say to the other, I'm sure glad that they evaporated. And after a certain time, after they condensate, they're turning back again to the solution. They say, we're glad. And then the other one said, then I'm getting out of here. Why? Because that one will also have at a certain time enough kinetic energy to turn into a gas. All right, important facts that we need to understand in equilibrium is what is an open space and the difference between an open space and an open system and a closed system. An open system is exactly what it says. It's a system which both energy and matter can be exchanged. So it interacts continuously with its environment, while a closed system is what we saw on the previous slide. There is no reactants or products can leave or enter the system. Okay. Okay, the gas molecules was the reactants and the liquid molecules was the with the we can just go back so that you can see here. The reactants here are the liquid, it's water, and the moment it turns into a gas, that is the product. Okay, that is the reactant and that is the product. It needs enough activation energy in order for them to change into a vapor. All right, and it must be in a closed system, so nobody, not the reactants or the products, can leave or into the system. What is a reversible reaction? In this reaction, as we saw on one of the previous slides, we have hydrogen gas and iodine gas, and it forms hydrogen iodide. Reactants form products and products form reactants. That is a reversible reaction when that can happen. Reversible reactions are represented with double arrows. So that is important that you only use this when it is a reversible reaction and no other reaction. Of course, you will not have any moles if you use that in a normal reaction. Now, what is dynamic equilibrium? It is a chemical equilibrium is dynamic because reactions do occur at equilibrium, but the system is balanced. So it refers to a reversible reaction in which the forward and the reverse reaction are taking place at the same time, same rate, and the concentration and of the reactants and the products are constant. So it's the same rate, the concentrations are constant of both the reactants and the products. All right, now what is phase equilibrium? Phase equilibrium, as you can see here, is at this stage there are more water molecules turn into a vapor than vapor molecules turn into a liquid again. Okay, into water again. So at a certain phase here, you can see then at a certain phase it can be the evaporation is less than the condensation, and at a certain phase both of them are at the same rate. So in A, water has just been poured into the beaker and the system is not yet at equilibrium. At B, all right, at B, equilibrium is reached at low temperature, and at C, equilibrium is also reached at a higher temperature. Both of them equilibrium, but low temperature, high temperature, and here it's not here. Okay, how do we establish equilibrium? Initially, the water evaporates and the number of molecules in the gas phase increases. All right? So the gas phase increases, the molecules in the gas phase collide and condense. Can you see that? So when the rate of evaporation equals the rate of condensation, a liquid vapor equilibrium exists, as you can see. So the level of the water remains the same. Here's a high temperature, the level of the water remains the same. Here there will still be a change. Can you see different level? The moment the equilibrium stays the same, the water level will stay the same. And evaporation and condensation still both occur. All right, but at the same rate when there is phase equilibrium. All right, now we have a graphical interpretation of equilibrium. The previous one was where it was only in one direction, the hydrogen and the iodine gas combine with each other to form the hydrogen iodide, while in this case we have an equilibrium. Previously it was not in equilibrium, or the reaction rate of the iodine forms to form hydrogen iodide was not necessarily a closed system. So what is happening here? Again, hydrogen and iodide is busy forming hydrogen iodide. But the hydrogen iodide can also happen. Hydrogen iodide turn into hydrogen and iodide gases again. But at a certain phase or a certain state, both of the reactions take place at a certain time and it will form an equilibrium state. So what is happening at the equilibrium state? The forward and the reverse reaction rate becomes equal. So hydrogen concentration of hydrogen and iodine is initially starting to decrease, and the concentration of the hydrogen iodide initially started to increase. The blocks around the hydrogen iodide, that is the symbol for concentration. You will see when you do other calculations this year by putting the blocks around the formula, it states that's the concentration of the hydrogen iodide. The rate of the forward reaction becomes constant and becomes equal to the rate of the reverse reaction. At this point, the concentration of the reactants and the products remain constant. All right, so this is how we explain equilibrium by changes in concentration of the gases. Okay, this is a graphical interpretation of equilibrium. This is a very popular chemical reaction that examiners love to ask. You can see here we have three different tubes with three different colors here, and this is the color. If we have D-nitrogen tetroxide, the N2O4 is D-nitrogen tetroxide, and the NO2 is nitrogen dioxide. Now the nitrogen dioxide is brown and the D-nitrogen tetroxide is colorless. Can you see here? There is colorless, that one is colorless and that one is brown, dark brown. Now what is happening here? Somewhere in between we have the two mixed together where there's an equilibrium. If it's an equilibrium state, the two mix, and then we have a color, a yellow-brown color. The color becomes darker as more N2O4 is converted to NO2. When the system reaches equilibrium, both N2O4 and NO2 are present. Both of them are present. That's why we have a lighter, a yellow-brown gas mix here. So not a mix. This is, can you see the hydrogen and the gas? Both of them are in the container. Then you have at equilibrium, you have both of them, and the color is, can you see, is yellow-brown. Okay, so a mixture of NO2 and N2O4 moves towards equilibrium. Colorless N2O4 reacts to form brown NO2. As the reaction proceeds towards equilibrium, the color of the mixture darkens due to the increase in concentration of NO2. NO2 is dark. At equilibrium achieved, the more NO2 that forms, the darker it gets. Can you see here? The darker it gets because it's colorless and the NO2. Factors which affect, sorry about that. Factors which affect equilibrium is concentration, pressure in gases, temperature. All right. Equilibrium will shift to decrease any increase in concentration of other reactants or product. So there will be a change in equilibrium in concentration. It depends on if it's an open system or a closed system. Pressure A change in pressure can be brought about by changing the volume. As I told you previously, when you use a syringe and you decrease or you increase the pressure, you decrease the volume of the container. Adding or removing one of the reacting gases changes the partial pressure of that gas and disturbs the equilibrium. You can also add or remove a non-reacting gas, but that will have no effect on the equilibrium. Temperature increases. The temperature of an equilibrium system increases the rate of the reaction. As we see previously, because there will be more effective solutions. About science clinic notes later on, but please look at the graphical interpretations and the science clinic notes, and also in your doxantial study. Factors which affect equilibrium. Here I do include a table for you to make it easier for you. If the concentration of the reactants increases, what will happen with the system? What will the system's response be? It will favor the forward reaction to increase concentration of the product. You have more to increase the concentration, so it will increase the concentration of the product. Change in the K value of equilibrium. Here you can see that and more about that in our next session when we do the calculations. If we decrease concentration of reactants, but there's a favor reverse reaction because to decrease the concentration of the products. If we decrease the concentration of the reactants, the reverse reaction needs more reactants, so it will favor the reverse reaction. If we increase the pressure, favor the reaction that produces fewer particles. If we look at our N2O4 and our NO2s, you will see that in our chemical equation, there's 2 moles NO2 and there's only 1 mole N2O4. So that is also an example that can be used to show the increase in pressure and the decrease in pressure. Okay, and then lastly is the increase in temperature and the decrease in temperature. The endothermic reaction will be favor when it's an increase in temperature, and decrease in temperature will favor the exothermic reaction. More about that in a minute. All right, and now Les Chatelier's principle is a principle to explain equilibrium. If we do have two people with similar weights, and as you can see here on the scale, then and here they are at equilibrium. The moment that we put more weight on this side, the scale will be unbalanced, and they will try to adjust. They will try to adjust so that the scale will be in equilibrium again. So what will they do? They can just give him one so that both the weights increases. That is an easy explanation for the Chatelier's principle. So if we change something in the system, and that's something that we can change, can either be temperature, pressure, concentration. Processes occur in the system, within the system, which tend to counteract change in those. So what solution did they have here? Do they have here? They just share so that he will also be, his weight will also be the same. So what will happen in a closed system? The system will react in such a way to counteract the change. So here we look at the equilibrium, and we can see the flask on the left is in a dish of cold water. The flask on the right is in ice. So what will happen if it's in hot water? Okay, so I always tell learners, all right, if it's hot, you want to move apart. Okay, so and what will happen if you move apart? You take the N2O4 and you make more NO2 because there's more space. It's hot. If it's cold, what will happen? You will move closer together, isn't it? The molecules will move closer together and more N2O4s will form, and so the reverse reaction will be in place. Dinitrogen tetroxide is a colorless gas. So N2O4, can see if it's cool, the gas will start to be lighter because more N2O4 is forming. If it becomes darker, it's increase in temperature, more NO2 is formed because NO2 is a brown. It's like brown gas mixture. Right. Increasing the temperature causes more NO2s to form and decreasing will cause more N2O4s to form. Again, see science clinics notes for more examples. Now the last topic that we're going to cover is acids and bases. And if I think about acids and bases, I think about the pH scale. And there's only one pH scale. We have the neutral that's in the middle, and you will have to your more red colors and you have more blue. Your strongest base on this side is sodium hydroxide. Your strongest acid, hydrochloric acid. On this side, and sulfuric acid are your strongest acids. Okay, they are on this side. All right. So now we have two definitions for acids and bases. The one is the Lowry-Bronsted that we normally use, and the other one is the Arrhenius. That's not so often used because there are some things that we cannot describe it with the Arrhenius model theory. Acids and bases are substances with opposite characteristics and are two types of corrosive substances, as we saw on the previous page. On the previous page, they are totally different in their reactions. If we think about litmus, red litmus and blue litmus will turn red in a strong acid, and red litmus will turn blue in a strong base. All right. So what is the Lowry-Bronsted theory? It is an acid is a proton donor and a base is a proton acceptor. So while Arrhenius is an acid produces hydrogen ions when it dissolves in the water, and the base produces hydroxide ions when it dissolves in water. So an example here is hydrochloric acid ionizes and forms hydrogen ions and fluorine ions. Sodium hydroxide dissociate and forms sodium positive ions and hydroxide negative ions. So the hydrochloric acid acts as a proton donor and the hydroxide acts as the proton acceptor. So it will accept hydrogen if the two of them combine. The hydroxide will accept the hydrogen to form water. The Bronsted-Lowry definition is, or Lowry-Bronsted definition is accurate for all substances because it is not limited to water as a solvent. When protons are transferred from an acid to a base, the reaction is called a proteolytic reaction or also proteolysis. So acid-base reactions, here you can see we have hydrochloric acid and water. And the hydrochloric acid donate a hydrogen for the water, and the water accepts the hydrogen and forms a hydronium ion and fluorine ion. And this process is called ionization, where the strong acids ionize almost completely in the solutions with with a high concentration of hydrogen ions. The sodium hydroxide, which is an alkali, dissociates nearly completely, becomes separated completely from the solid state in sodium ions and hydroxide ions so that it can combine with the hydrogen to become water again. Acid reactions are reactions during which protons are transferred. So we have an acid with a base. These are four the most common used chemical reactions that you need to write. So you need to know if I do have an acid and a base, it will form a salt and water. Um, in this case, we have if sodium hydroxide and hydrochloric acid react with each other, you will have sodium chloride, which is table salt and water. So that is the reaction for the acid and the base. Acid plus a metal oxide will also give the salt plus water. This is a metal oxide. This is an acid. All right. So again, if these two react with each other, we have salt and water. The salt will be sodium chloride plus water. And acid plus a metal gives a salt plus hydrogen gas. As we saw previously, the magnesium metal and the sulfuric acid or magnesium sulfate, that's the salt, and hydrogen gas. And acid plus a carbonate gives a salt plus carbon dioxide and water. Make sure that you know these reactions and that you can write these reactions. You can also see the science clinic notes for that. All right, acid-base pairs. In the Lowry-Bronsted model, an acid is a proton donor and a base is a proton acceptor. Okay, so what? Give an example. The HA and A negative is called an acid-base pair. The acid that donates the proton will turn into a conjugated or will form a conjugated base. All right. An example. There are few examples that we do have here. We have protons and conjugated bases, a chloride, nitrate, hydrogen sulfate, and water. Conjugated acids are hydroxide plus a hydrogen ion will form water. These conjugated acids are weak acids. All right. These are very strong bases will give you weak acids, while strong acids will give you weak bases. All right. So here we can see what I talked about. We have a strong acid and we have a weak conjugated base. And we have a weak acid and a strong conjugated base. Water is a weak acid. Substances such as water and hydrogen sulfide can react as both an acid and a base, and therefore they are amphiprotic and are called amphipolites. Calculations of acids and bases will be done with their chemistry. So, last, I just want to add again the additional resources, make notes, and make you aware, the learners that didn't attend last week's session, there are additional resources, the doxa resources. It's the study guides that we've been using, that you have summaries in it, mind maps in it, and the question papers are the question papers that I give to you or are in the handout box today. So please make sure that you download the question papers and the memorandums you can download from the guided learning platform. There are also exercise books that you can buy from Drug Center and past exam papers that you also can buy from them. All right. Now the Quanta books is the books that are part of your packages this year. Please, learners, make sure that you make use of the DVDs. It's a excellent qualified physical sciences teacher explaining the, the concepts, the most difficult concepts for you on DVD. It's small snippets, it's 10-minute lessons. So please go on the links. There are a total of 8-hour lessons. So, but it's small lessons combining in a total of 8 hours. So please look at the DVDs if you are not sure about a certain aspect or term. Go on and look at the DVDs. Now the Quanta books do have a small summary in, but the most important part are the question papers. The questions, the longer questions and the multiple choice questions. When we write them at the back of the book, and the multiple choice questions are explained. So please, if you do have time, make sure that you do 3 to 5 questions each day, and multiple choice questions, just to make sure that you remember all the work that you're busy doing. I know the syllabus is very, very loaded, so make sure that you do a few questions during the week. Okay, then the science clinic notes and the exam seminars are the Science Clinic notes are free smart prep books that you can download from the website. Make sure this is the link that you can use to download the smart prep books. After the session, it's very valuable notes and it's summaries. It's both for physics and chemistry and all the information sheets that are necessary for this year. So please make sure that you use that and download that. They also have exam seminars during the year that you can take before the prelim and end of year. I'm not sure about the June exam, but as we will see what the lockdown will do. But go on the website and see where they are in events. It's nationwide. They do have venues where they do the exam seminars. Go on their website, register for the exam seminars, and you will see and register for them. So that is very essential for you to help you to get through your work as well as exam preparation till the end of the year. All right. If you do have any questions, please remember to write your questions now in the question box or send an email to academics@impact.co.za so that I can attend to your questions. And if you are not registered with Impact, you can contact us at info@impact.co.za. The Impact learners, remember you can download memorandums from the guided learning platform as well as the PDFs from today, and you can all go onto the Impact YouTube channel to download the videos from the webinars we do during this time. So thank you very much for your attendance today. And if you do have any recommendations, you are more than welcome, or suggestions, you are more than welcome to send that to me as well. Have a nice day and God bless. Thank you. Bye. While we're waiting, so please remember to ask your questions in the question box and download the notes from the from place where you can download it. Okay, the handout. And any other questions from the computer academic agenda?